Okay, so this is week number 11, and any questions from the previous session, week 10? Okay, then let's move on. So this week is all about solving two equations. One is Laplace equation, which is in fact a generalized case of a Poisson's equation. Okay, so Laplace equation, as we all know, is in general grad square phi Laplacian of phi is equal to 0, and in this case the Poisson's equation is some function, right, which we don't know, and this could be in any dimension 1, 2, 3. So in 1D this is just second derivative, right, equal to 0, and with this we can solve, right, we can integrate twice so that phi of x is a linear function mx plus c, and to determine this coefficients we need boundary conditions, and in 2D this will be del 2 phi by del x2 plus del 2 phi by del y2 is equal to 0. 3D you have one more term, right, this 2 plus lz2 is equal to 0. Alright, and here it's the same thing, but only difference is that on right hand side you have some function of x, y, z depending upon how many dimensions you are in. Okay, so how do we solve that? Before that, let's recall one basic thing. Recall, which is how to discretize this second derivative, right? So d2 phi by dx2 at some point I. So what we have is some points. This is I plus 1. So this is xi, in fact, xi plus 1. This is xi minus 1. And there is some curve passing through this, but we really don't know what it is, right? We just know the values at this point, and we want to find the second derivative at this point. So we say that let's first find the right derivative, which is del phi by del x plus, let's call it first, at I, which is looking here and find the derivative. It's same as saying we are standing at the middle of this point and looking at the derivative using central difference. Okay, so that is going to be xi plus 1 minus xi divided by h, where h is this distance between two consecutive points. Alright, similarly we can write the derivative in the negative direction, which is if you are looking backwards, if you remember, so that's the slope between these 2 points. So that will be xi minus 1 upon h. Now the second derivative is like saying that it's a derivative between these 2 points. So we kind of evaluated derivative here and here, and second derivative is the derivative of this first derivatives. So it's going to be the right hand derivative minus left hand derivative. Okay, and the distance between these 2 points is again h. It is divided by h, and right hand derivative is xi plus 1 minus xi upon h, minus this is xi minus xi minus 1 upon h whole divided by h. So we have h square on downstairs. Upstairs we have xi plus 1, then xi minus 1 and minus 2xi. Okay, so this is the approximation for the second derivative, right? At point x is equal to xi. Okay, this is the approximation. Well, so what are we saying in case of Poisson's equation? That this is equal to 0. Okay, so sorry, Laplace equation. Okay, so what we can do, so in 1D we already solved it analytically, so we are not looking at it. Even if you solve using this method, you will get a linear solution. In 2D, however, 2D, we have grid of points, right? So this is phi at 1, so phi 0, 0, phi 0, 1, phi 0, 2, etc. Then phi 1, 1, phi 1, 2, etc. So now we want to solve the equation on the entire grid. For that, we will leverage some properties of Laplace equation. So properties, alright. One is that it's unique given boundary condition, and boundary condition could be of the form phi of walls is equal to something, right? And this is called Dirichlet, or we can specify the derivative gradient of phi in the direction of the normal to the walls. So maybe I should write n cap here. Okay, that is given something, and that is Neumann. Okay, or you can have mixed, in which case on some parts of the walls it's the value itself, on other parts it's the gradient of phi which is specified. So if the boundary condition is specified, then there exists only one solution which satisfies the Laplace equation. Second, which is the average theorem. So average at center is equal to average over the sphere. Okay, in 3D. In 2D it's disk. And in fact, the sphere can have any radius less than whatever the region that is specified. So in fact, in discretized version, it means that phi ij is average of its all its neighbors. How many neighbors does it have? If pi ij is here, then you have this one, right, left, up and down, 4. So it's phi I minus 1j, phi I plus 1j, phi ij plus 1, and phi ij minus 1. Okay, so it's like that saying that goes like you are the average of the 5 people you stay with. Okay, so if you are staying with a poet, someone is a poet, one is angry person, another is a scientist, then you end up being average of those 5. Okay, I don't know if that is true, but that's true at least for these harmonic functions, which are the solutions of Laplace equation. Okay, and the third thing, which is that solution cannot have maxima or minima in between. Minima in the interior. Okay. So in 2D it's easy to visualize. Suppose your boundary condition is something like this, and if your solution is like this, it's difficult to draw, but imagine there is a peak in between. Okay, there is a peak here. Then it would mean that the gradient square, the Laplacian, would be negative, right? And that is not allowed because it is supposed to be 0, so it can't be negative. Similarly, you cannot have any minima, a dip, right? Because then the Laplacian would be positive. So that's why you cannot have maxima or minima, and that
Can you just explain this, please, in detail? Like how the maximum becomes uh, less than zero, negative.
yeah. So let's take one simple. First, let's take 1D example. In 1D, you have a function, and what's the condition for minima? That's first is that f dash of x should be 0, right? The slope should be 0, because if the slope is increasing, then you go leftwards, you are going down, so it can't be minima. Okay, and there is another condition, which is that double derivative should be positive. Why? Because it should be curved up, right? It should be convex. So and for maxima, the double derivative is negative. Okay, now suppose there is an equation which is this one. That means it cannot have minima or maxima. Okay, now what is the function in 1D? I have specified the boundary values. Let's say at a and b it's this. I cannot have maxima or minima. Okay, it is the linear function. So of course you can have other functions also which does not have maxima or minima anywhere. But the thing is that whatever the solution is, that cannot have maxima or minima. Okay, and that is, so the straight line obviously does not have any maxima or minima. Okay, now we can generate, we can use the same idea in 2D. Imagine a paraboloid, right? So it's like this. It's very difficult to draw, but you can imagine there is one parabola, okay, and it is rotated around z-axis. So what would be the formula for this? It would be x square plus y square, something like this, right? Because just for x it would be x square, and then for y it would be y square, and you are rotating, so you want it to be symmetric. So this is same as saying is equal to rho square in cylindrical coordinates, right? And now if we take a second derivative, so great del square z, that would be del 2 by del x2 x square plus y square plus del 2 by del y2 x square plus y square. So now when we differentiate this with respect to x, it's 0. Similarly, this term is 0, and x square when differentiated twice will give 2x and then just 2, and then this is equal to again 2. Okay, so in fact this says curvature, this Laplacian is equal to 4 everywhere, which means it's always curved upwards, right? But at the bottom it's definitely curved upwards. So the minima has positive value of this one. Okay, that's the idea. Is it clear?
Yeah, yes, thank you.
Yeah. So I haven't given a proof. I don't think I can prove it, but that's the intuition that whenever you have a peak or trough, this cannot be equal to zero. All right. Okay. And then the first method that we did was this direct method, and it wasn't explained in great detail because we are not going to use it, right? But just to give an idea, I found this for a 4 cross 4 grid. So you have 4 points, 4 by 4, 16 points, and it starts from 1 1. So 1 1 1 2 1 3, etc. 1 4. So what you can write is equation for each ij similar to this one. Okay, and then you can write in matrix form. For example, for 1 1, you have 4 coefficient for this one, and then minus 1 for each of the neighbor. So this gets minus 1, this gets 4. This 2 1 will also get minus 1. So this will be minus 1, etc. Right? So for u11, 4 is u11, then this minus 1 is u21. Okay, that's this one. And then there is minus 1 ahead of u12, which is here. So you have 4 minus 1 minus 1. Similarly for u21, you can imagine it has 3 neighbors, right? This 3. So for u21 itself it's 4, and then it has 3 neighbors, so 3 times minus 1. And those who are at the middle, this have 4 neighbors. For example, this one, no, not that one, this one. So this is the self term, and these 4 are the neighbors. Okay, and this entire thing is equal to 0 for Poisson, sorry, Laplace. Okay, so it's a matrix equation. It's very big, but it's solvable, right? Anyways, we are going to do this next week, how to solve matrix equations. Okay, and if it is a Poisson's equation, then you have some terms here, but again, then you can just solve it because it is just x is equal to b, which means x is equal to a inverse b. Okay, these are vectors, this is matrix, so it's just one step. Of course, calculating a inverse itself is a big task that we need to do, but if you can do it, then you can solve it. Okay, then the second method, which we are actually going to code, is Jacobi. And the idea is that, well, you can write that average equation. It is phi ij is equal to 1/4 of phi I minus 1 j plus phi I plus 1 j plus phi I j plus 1 and phi I j minus 1. Okay, so and now you do basically iterations. Iterate this again and again. So if you can recall, the relaxation method was, if you have xn plus 1 is equal to f of xn, and if you iterate again and again, you get a value of x star, which when applied to x star gives almost equal to x star, and that was fixed point. of this map F. Okay, so it's a similar kind of thing. We will do this again and again, but now we are applying this on the entire grid. Okay, so for all the points we will apply this law. Okay, and then we'll update the values. So now we have new grid values. Again, do the same thing. Let every point look at all of its neighbors and update it to its values. Okay, and you can keep on doing that. And a good idea is to vectorize this. That way you can accelerate the process. Okay, so this is the Jacobi. So in this case, this is the new one, right? The updated one, and these are the old ones. And that's essentially the Jacobi method, and we'll do coding for this. And then some smart guys come, Gauss, Seidel, and they just say that, okay, why are we using old values for this one when we have some of the updated values, right? And we know that updating makes you closer to the real solution. So when you have the updated values, use it. When you have updated value, just use them. Okay. So now phi ij new is again the same thing. I'm not writing entire thing. Same as previous. Only difference is that if they are updated, use them. Okay. Which means we are going to update this sequentially. First we'll do 500. Okay. Then when we do 510, that will be 1/4 of 500. Then 520 and 520. I think only two, right? And 501. Yeah, only three because it's on the wall. Okay. If it is, let's say, 1 1, then it will be 0 1, then 1 0, then 2 1, and 5 1 2. Okay. So in this case, the 0 1 1 0 would already be evaluated. Okay. So this two will be updated one, and this two would be old because we haven't updated. When we go to this one, we need to use 5 1 1. That we will use as this one, the updated, because we have it available. Okay, so that's good, but there is one minus point, one con. We can't vectorize, right? Why? Because we are not using the same values for each of the updating values, right? For each iteration, we are using different values. Okay, and then the fourth method, fourth and fifth is fourth is red black, and the idea is that you can divide the grid into two kinds of lattice, if you can call it one. Okay, so you have red points like this, and then black points. And then for updating the red ones, you only need the values of black ones. You don't really care about red ones, right? Similarly, when you are updating the black ones, you only need the values of red ones. Okay, so you kind of have two separate groups, so you can think of them as independent groups, and that accelerates the process. All right. And the last one is SOAR, which is successive over relaxation. So what is relaxation? What we did with Jacobi, right? That phi ij new, this is new, is 1/4 of neighbors. Let me just write neighbors. Okay, that was the old way. Now we say it's some omega by 4, where omega is greater than 1. Okay, so this term is higher. And to compensate that, we say it is plus 1 minus omega times phi ij old. Okay, so and this omega is greater than 1. In fact, between 2 and 1. So this is negative. So what we are doing is kind of we when we are relaxing, we are going to some kind of equilibrium point, right? So we have ball here and we go in the direction of gradient, go like this, and we have some steps. That step is this one. What this method is saying is that maybe we can increase the step size. Okay, then what's wrong with that? Well, if when you are close to fixed point, you can overshoot, right? So to prevent that or to rectify that, we also go back in the direction of phi ij, the old value. Okay, and what value of w should be chosen? That's subjective. You have to look at the problem, and there is no w star. Okay, that just works the best for any problem. Okay, so if the ideas are clear, then we can move on.
This W in for both it will be in the range of 1 to 2. Like means W by 4 neighbors plus every time it is in the range of 1 to 2. Just
Yeah,
to take the next step, one step back, it is in the range of 1 to 2.
yeah. So the value of w is between 1.1 to 2. So let's say it's 1.5. That means in every step you are going to do 1.5 divided by 4, which is how much? 1.5 by 4 is 15 divided by 4.
0.375.
Yeah, so 0.375. So it is 0.31375 neighbors and plus 1 minus w. 1 minus w is zero point 0.5. Okay,
But here now when we say, okay, okay, yeah, yeah, got
okay.
it. Yeah.
But this has four terms, right? So in all of the four terms, this is being multiplied. So if we do 4 times 0.375 and minus zero point 0.5, what do we get? We get 1, right? So whatever we are adding, we are removing some terms, but we are adding more contribution to neighbors and we are removing the contribution from phi itself. Okay, that's why we are doing over relaxation. So more than relaxing. Does that answer your query?
Yes, yes,
Yeah.
yes.
Okay.
Okay.
Okay. And the last point for Poisson, again the second derivative is whatever it was earlier. So, but this is second derivative, yeah, and that is equal to some function. So this again you can write in terms of ij, right, where I is equal to 1 to n, j is equal to 1 to n. So again when you rewrite, and this can be written as phi ij. Okay, this is some function of this. So when you rewrite this, what you get is phi ij is equal to 1 by 4. Again neighbors, phi I minus 1j plus phi I plus 1j, phi I j minus 1 and phi I j plus 1. And there is an extra term due to this f, which is h square by 4 f ij. Okay, and this is the extra term. And clearly, if f is equal to 0, then we get our Jacobi method, right? The conventional way. So this is the modification that we need to remember. Okay, so shall we move on to assignments?
This h square by 4 comes because of the average of that set. Means if we take Laplace and then divide by h square is there, and on the right side 4 is already. How this 4 comes in the second term, extra term?
Okay, let's just do it properly. So del square phi is del 2 phi by del x2 del y2. Okay, now this is phi I plus 1 plus phi I minus 1. So there is a, and minus 2 times phi ij, right, divided by h square, and plus this is going to be where I is constant now, so it is j plus 1 plus phi I j minus 1 minus 2 phi h divided by h square, and this is equal to f ij, right, because here it is just f of x comma y, so that becomes f ij. So now h square can be taken common, and phi ij has total 4 contributions. So this is like neighbors minus 4 phi ij is equal to h square times f ij, which means now we can rewrite it in terms of phi ij, right? So this term goes to left hand side, so it becomes neighbors minus h square f ij, and that is equal to 4 times phi ij, so we divide by 1/4. Okay, so to answer your question, we have h square in both the terms, that gives the h square, and 4 phi ij because there is one for x derivative, and there are two for x derivative and two for y derivative. Okay,
Yes, yes.
yeah, and now you can imagine if you had 3D function, then it would be 6, right? Okay, but we are not doing 3D, we'll do 2D. So let's first do this little cute questions, then we'll go to coding. Okay, first one is, what is the solution of 1D Laplace equation and the boundary conditions are given? Is this Dirichlet or Neumann? Well, it's mixed, right? Because this is derivative and this is just the value. So how do we solve it? There are multiple ways. One, which is the straightforward, is that uh, we have this equation is equal to 0. It should be 0. And we know that solution is phi of x is equal to mx plus c, right? And now we have two unknowns, but we have two conditions, so we can solve for it. So phi of, let's do the first one. Phi dash of 0 is going to be derivative of this, which is just m, is equal to 1, which means phi of x is x plus c. And now phi of 0, sorry, phi of 1 will be 1 plus c, and that is given to be 0, which means c is equal to minus 1, which means phi of x is mx plus c, m is 1, so x plus c is minus 1, so x minus 1. Okay, option number 2. Other way to think about it, which is almost equivalent, is that you are given, so we have 2 points 0 and 1. We know that at 1 it is passing through 0. Okay, and we are given the slope at 0, but we know that it's straight line, so slope is 1 everywhere. So it's a line of slope 1 that is passing through this 1 comma 0 point. What is that line? So if slope is 1, then it is x, and then the y-intercept is minus 1 because it's 45-degree line. Okay, so it is x minus 1. Both of them are exactly identical. Okay, let's proceed. If you don't understand, please do interrupt me. Okay. Which of the following describes Dirichlet boundary condition? A is constant and n cap is the unit vector normal to the walls. This you can answer in the chat box. First option, so Dirichlet boundary, phi of walls is given, derivative at walls, the normal component is given, and the second derivative is given, and none of the above. Answers in the chat box. 1, 1, and 2 was for, I guess, the previous one. Yeah, x minus 1. Nice. Okay, so for this one we have 1 by Tanuja and Sovik, and that is in fact the correct one. Yeah, so Dirichlet is when phi of walls is specified. It need not be constant, okay? In this case it is, but it can be anything. And this would be Neumann. Okay, third one, which also I think you should be able to do. Which of the following satisfies the Laplace equation? So one is 2x times 2y square z cube. I don't know why they wrote it like this. This is equal to 4x y square z cube. And the second one is x square plus y square minus 2z square plus 10. So let's see if somebody can solve it. Question 3, 2. Okay, what is 2? 2 is 2. Okay, let's see. So we want to find this quantity, right? Which is del 2 by del x2, 4x y square z cube, plus with respect to y, same thing, and with respect to z, same thing. With respect to x, when we differentiate once, we get 4 times y square z cube. That does not depend on x, so we get 0. For this one, we can treat rest of the x and z as constant, right? And y square second derivative would be 2y and then just 2. So this will become 8 times x z cube. And the third one, for that we can consider this to be constant, only z cube is to be differentiated. So that gives 3z square and then 6z. So that becomes 24 x y square z. Okay, and clearly this is not equal to 0. Okay, what do I mean by that? For all x, y, z. So this has to be 0 for all of them. Okay, just some solutions won't work. So clearly if x is equal to y is equal to z is equal to 1, for example, then it's non-zero. Okay, so that does not satisfy Laplace equation, which means that will never be a solution to Laplace equation. Okay, second one. So again, now we can break it into these three terms. So the x derivative will have contribution from this term alone. Similarly, for y, we have only this term. Alright, so this will give 2. As we discussed, the second derivative of x square is 2. Similarly, this will be 2. This will be minus 2 times 2 because we have factor of 2 outside. So this just becomes 2 plus 2 minus 4. And this will just give 0, right? It's just constant. So we get 0. Okay, so only 2 satisfies Laplace equation. Correct answer is 2. Yes, Tanuja. Okay, next question. In 2D, a potential is given x square minus y square that satisfies Laplace equation. I don't know why they need to give it to us because we can clearly see, right? This is second derivative is 2, this is minus 2, so sum is 0. So we can verify that. What is the average value of V over a disk centered at 0, 0 with a unit radius? So we know the average theorem. It says that it should be equal to the average value should be equal to the value at the center. 1, 1. Nice. Yeah. So what is the center? Center is 0, 0. So average is equal to value at the center, which is just 0 square minus 0 square. And last time I checked, it's equal to 0. Okay. By the way, even if you didn't know the theorem, it's not very difficult. What does average value mean? It means integral over area element, right? So x square minus y square dx dy over the disk, the unit disk, which is symmetric in all the four quadrants. So we can just write this as disk x square dx dy and minus y square dx dy. But what is x square and what is y square? That depends on how I define it, right? So if this is x and y, then x is read like this. But I can flip this so that this becomes x and this becomes y. But since this is a disk, its shape does not change. And now I can read the values like this, and it should be same, which is the value of average value of y square. Okay, so by symmetry, these both are equal, which means the average is 0. Okay, nothing to do with this week's equation, but in general, when you have integrals of this kind, you should be able to see the symmetry. Of course, you have 1 over area here, which is equal to pi times 1 square, but the answer is 0. Okay, now we have two questions, coding questions. So let's go one by one. First is Laplace equation. Grid size is given 128 times 128. And it's given that not including the boundary. Okay. So the boundary point should be outside the grids for a potential phi in charge-free region using Jacobi method. And we have to find the value of phi using the tolerance. So this tolerance specifies when to end, right? Where to end. At third grid point from the right boundary and second grid point from the top boundary. And now the boundary condition is given. The left wall is kept at phi is equal to 4 and 0 elsewhere. Elsewhere as in the other three boundaries. Start the iteration. Again it's given. I don't know why it's specified twice, but that's okay. And at the end we round off to 2 decimal place. Okay. So before we start, I need to draw your attention to two things, which is how we imagine matrix versus how we imagine Cartesian space. And to be honest, even I hadn't paid much thought to this earlier. So this is our Cartesian space, right? This is 0. And let's say I want to go to point 10, comma 2. Then that is equal to x is equal to 10 here somewhere. Okay, so this is 1, 2, etc. And 2 would be somewhere here. So this becomes 10, comma 2. Okay, now imagine I have a matrix, this matrix, and I want 10, comma 2 element. So then I'll go to 10th row. So I'll go down 10th row. Maybe this is first, second, etc. And the second column. It will be somewhere like here. Okay, so our origin in matrix is this one. This is our I value, right? And this is our J value. Okay, and that's definitely different than how we imagine points in Cartesian. So that we need to remember. For that, we'll do some little kind of research to see. We'll plot the solution. Okay, so let's start. First, let's specify the parameters. N is 128, and then the solution is on a grid, right? So the grid has size of np dot zeros, n comma n. That would be our naive thinking, but we are given that we are not including the boundary. So the boundary will have extra 2 points, one on left, one on right. Similarly, one on top and one on bottom. So 5 will have zeros of n plus 2 and n plus 2. Okay. And then we need to specify the boundary condition. For that, let's just plot a matrix. Okay, so let's say we have a matrix which is this thing np dot zeros. And how can we imagine the matrix? We want to visualize it. One way is to plot it using plt.matshow. So it shows the matrix. So let's do that. Let me run it. And it gives this purple thing. Okay, because it's everywhere 0. So we want to know what the value of purple is. That's why we put color bar. So plt.color bar. Okay, then it gives this greenish value, which is we know it's 0. Okay, and now we want which wall to be for? Left wall. So what should be the left wall? So let's just try one thing, which is 5 of 0 comma this is equal to 4. Okay, so I'm setting this I to be 0 and rest of it to be 4. Why is it not showing? Let me make it 0 to 2. Maybe it's too thin to visualize. Oh, this should be M. Okay, and we see that the top line is getting yellow, which means the index 0 corresponds to this 0. Okay, let's just confirm that. maybe. Okay, maybe it's too thin, but let's move this to 3. And then we see the line at 3. Let's move this to 40, and it is at 40. But if it is at minus 3, then it's 3 from the bottom. Okay, so that way we are sure that the first index corresponds to this horizontal lines. Okay, and just to make sure we are not doing any funny business, let's change the value with the second index, maybe 2, and it plots line here. Okay, so the second index is this one, and now we want 4 value at the left wall, so exactly at 0. So we write m of nothing comma 0 as 4, and sure enough it gives this yellow line at the left wall. Okay, so this is what we want. That's why we write phi of sorry nothing comma 0 is equal to 4. Okay, this is our initial condition rather than boundary. And then let's write some parameters. One is the tolerance value, which is given to be 10 to the power minus 6, so 1 e minus 6. And then error, so we want to enter the loop. What will be the loop? While error is greater than EPS. But to enter we need some initial error, which can be any number higher than epsilon, so that we enter. Once we enter, then we'll calculate the errors and we'll get the answer. So we can just say EPS plus 1, or you can make it 10 or infinity, whatever. NP dot infinity, right? Anything else that we need? Yeah, I think it should be okay. Now we say phi new. Phi new itself will be not NP dot zeros. Yeah, so first we save a copy phi new or phi p, as professor has mentioned. And phi p is just copy of phi. Okay, and then we can update phi p, but we would only update the interior points, not the boundary. So that will be 1 to n plus 1, comma 1 to n plus 1, and that is going to be 1/4 of the neighbors. Okay, this we have neighbors. So let's write the neighbors of the old array, which is phi of. So left neighbors would be 0 to n, right neighbors will be 2 to n plus 2, and then the top neighbors, yeah, it already gives. Top neighbors is going to be, no, this is not correct, is it? No, it's just 1 to n and 2 to n plus 1, and the down neighbors would be 1 to n and 0 to n. This will be n plus 1. Okay, and error is the difference between phi and phi p. So we take that difference. Okay, for each of the grid point and take the absolute value and take the maximum. So maximum error between the old phi and new phi is this one. And then we need the copy of this. So we write phi as phi p dot copy. Okay, so this new p is saved as phi, which will serve as old phi for the next iteration. And anything else? Let's just run this. I think that this should do. 128 and 130. So 0 again, 0 to n. Oops, I forgot. This should be 1 to n plus 1. 1 to n plus 1. Then 1 to n plus 1. This will be 2 to n plus 2. Okay, it's running. So now we can comment this and plot phi. Okay, and then we see that yellow line, the boundary has now spread into the region, and there is a gradient from 4 to 0, and that gradient is sharper on the towards the top and bottom boundary, because at boundary it's supposed to be 0, right? So we see this kind of parabola like contours. Okay, and then what are we asked? Where should we find the value phi? At third grid point from the right boundary and second grid point from the top boundary. Okay, so to do that, let's again first copy this. Let's find out where these points are. Copy. Okay, we want third grid point from the right boundary and second from the top boundary. Now the third grid point from the right boundary is decided by the second index. Okay, and that index is going to be, so -1 is the right boundary, and then we have to go 3 more, so it becomes -4, and second from the top boundary, right? Second from the top, yeah. So the top boundary is 0, then first is first, second is second. So if I make it 4 and then plot it, let's see if we are getting the correct point. Yeah, third from the right boundary and second from the top. So it's somewhere here. So we want the value of 2 comma value of phi at this location. So let me just print. Why should you kept the previous phi of 2 comma -4? And that is very small, right? As we can imagine, 0.00156, because it's close to this, and we know that here it's very close to 0, almost purple. So this is the answer, 0.001567. Unfortunately, that's not the answer given in the solution, and it turns out they are
Sir,
talking about some different point. Yeah.
sir, if you follow professor's code, he
Hmm.
actually approached from some other point.
Okay.
If you change the phi input,
Yeah.
means Yeah, if you put that 0 just in the left position, you will just see the change because he is using contour font, which actually transposes the matrix.
Okay, you are right. We can do transpose and everything, but the fact remains that you are at the right wall, right? You are very close to right boundary, and only the left boundary has this non-zero value. So you are very far from the boundary which has the value of 4, and therefore your answer must be very close
Well,
to
one
0.
more thing, and
Yeah,
hello, sir. One more
yeah, yeah.
thing that the question it's asking is might be from means 1 to m minus 1 means the matrix before the last matrix. Sorry, the row before the last row.
Row before the last row.
Yeah.
So you are saying I should put -2 here.
No, 1 comma minus 1.
Yeah, if you put 1 comma -1, then you will get what is asked. No, again it's 0, because let's see where is 1 comma minus. So -1. So the second one is the this column,
Yeah.
the column. So -1 would mean the last column. One is means it's the first row
You can
rather the second
interchange
row.
the position means you
Yeah.
can write minus 1 comma 1, you
Uh-huh.
will get that position. 1 comma minus 1. Yeah, yeah,
-1
same.
comma 1. Yeah.
Yeah.
Then you get this point. Okay. So the yeah, that should give non-zero value. -1 comma 1. Let me run this again. Then this. Now that also gives 0. But I'll tell you which one gives the right value. It is 2 comma 2. That also does not give the right value. 2 comma 1 gives the right value, I think. Yeah, that gives 2.79, which is probably there in the question. Yeah, 2.79. Okay, but this is incorrect according to the question, because let's locate 2 comma 1, and I'll tell you how I got 2 comma 2 comma 1. It is this point. Okay, so it's close to the left wall, so it gives a high value. But the reason that is not correct is it's because it's very close to, in any notation, in any convenient system, it's close to the wall that has non-zero value, and that is not what is asked is in the question, right? In the question, which is in English, left wall is at 4 and other walls are at 0. So if you are close to the other walls and far from left wall, which is what is given in the question, right? You are very close to the right wall, so your answer must be close to 0, which is why this is not correct in my opinion. All right, but if you are confused, that's all right, but they have rectified this in this year's question. Do I have it? This is this year's, right? Yeah, this year's they are simply asking you to evaluate it. Boundary condition is also given in terms
Yes,
of
sir, it's same.
indices.
You see, it's if 0 is is equal to 5. It's in giving the left boundary as
It's
if
not
0.
mentioned that this is left boundary. This is a different question. You see,
Sir, the approach is still the same, no?
Approach is still the same, and if you use this code, sorry, this one, and you put the value that is given, you get the correct answer. Okay, because in this case there is no question of left right. Everything is just indices. So you blindly follow what is given in this. F of 0 comma nothing is 5 and other things are 0. And at the end you have to evaluate f of 1 comma minus 3. So I can't do that in front of you because we are told not to do
Yeah,
that.
yeah, yeah.
Yeah. But if you change this to 5 and if you change to 3 minus 1, whatever it's given, it spits out the correct answer. Okay. Okay. Should we move on? Okay. So the second question, which is again similar, it's just Poisson equation. So on right hand side we have an equation. This is exponential of r square. Let me make it in LaTeX. Yeah. Okay. So it's exponential of minus 24 r square in a 2D box, minus 1 to 1, minus 1 to 1. Okay. Now the box size and everything is needed because we have on right hand side some quantity that depends on x and y. Okay. And the grid size is 64, smaller. Again, grid excludes the boundary, and now the boundary is that everything is at 0. Okay. So this is allowed. By the way, in this case, if the boundary was everything was 0, then what would be the answer? It would be that just everything is 0, right? Because that is a valid solution, and we know from uniqueness theorem that there is only one solution. Right. So that becomes trivial in case of Laplace equation, all the boundaries being kept at 0. But in Poisson's equation, that still is non-trivial, and we have to solve it. And then again, we have to use Jacobi iteration, and we have to find phi at some point. Okay, so in fact, I think I can copy paste this. We have to modify just few terms, right? So let me copy paste this. One is that I have 64 grid points, and now I have a function on right hand side. So let me define the function first. Should I call it f or g? Yeah, f. Define function of x comma y. Yeah, it spits out this thing. So np dot exponential of minus 24 x square plus y square. Yeah, r square is x square plus y square. And now we need to find fij. For that, first we define the linspace. So x is np dot linspace from minus 1 to 1 with n plus 2 points. Again, because grid points are excluding the boundary. So if I'm including the boundary, I have 2 extra points. And y is this one. And phi is going to be, first we need fij. So let's do that. So f itself is going to be zeros. So some matrix of dimension n plus 2, n plus 2. And then we need to fill in f, right? So for I in range n plus 2, for each x and each y in this array, fij is going to be f of xi and yj. Okay, so this gives us a discretized version of fxij, discretized on this mesh. Alright, now phi is going to be the same thing, and this is still 0, so we don't really need to specify it. Okay, I'm using MATLAB commands for some reason. epsilon is still 10 to the power minus 6. Error is this. Everything is same. And now I have one more term, right, that we discussed. 1/4 of h square times fij. So 0.25 times h square, which I forgot to define. H square times fij, and ij is the vector from 1 to n plus 1 and 1 to n plus 1, right? We are excluding the boundaries. Okay. Now what should be h? In this case, so h is the grid size, right? So our grid is from -1 to 1, and we have n plus 2 points. So the difference is 2 between the endpoints, and in total we have n plus 1 intervals. Okay, so it should be h is equal to 2 divided by n plus 1. And while this is, now let's run this. Sure enough, there is error. Exponential minus this thing. Oh, maybe it's confused. Oh, I kept the same name. So let me call this G and G. So I gave the same name to the function and this matrix. Let's run this again. Yeah, now it runs. Now let's first plot the solution. So plt dot matshow of phi. Okay. And then color bar. And it gives this thing which is circularly symmetric, right? Why? Because the function itself was circular symmetric and the boundary condition was all zero, so again symmetric. And you are right, ideally I should do transpose etc, but in this case it's not needed. Okay, because I can locate a point here or here or here or here, anywhere it's going to be the same. Okay. So in any quadrant it's going to be the same. Now where are we asked? Second grid point from the right boundary and second grid point from the top boundary. So this does not matter which boundary it is in this problem, right? But still, let's use our finder algorithm to find these points. So first we want from the right boundary it should be second grid point. So this will be -2, and from the first from the top boundary it's second. So this will be 2. So it should be 2 comma -2. Right, and that gives this point which seems correct, right? Second from the top, second from the right. So I can print phi of 2 comma -2. We have to round it off. Yeah, round off to 4 decimal places. So and p dot round to 4 decimal places. That gives -0.001. Okay. Why? Because again we are very close to boundary, which is kept at 0. So it has to be very close to 0. And it's negative everywhere, as you can see. Why? Because the function itself is positive. This is positive, so the second derivative is positive, is like negative curvature everywhere, which means it is bulging downwards, and the walls are kept at 0. So everything has to be less than 0. That's the idea. The answer is 0.001, which is not there in the problem, but we have plus 0.
Actually, a
Yeah.
similar thing means this is not there in option you are telling, na?
Hmm.
In the
But it should be
means
minus.
similar thing for this type times assignment also. Just I was trying instead of this grid point 64 when we means H if we take 65, it comes
Yeah.
one of the options. So why is that I was not able to understand.
No, I think if you do h is equal to 64, then you get one of the options, right?
H is equal to 2 by 64 we should ideally take, but that will not give the options available. So if
No,
we
no,
take 2 by 65,
no, I think you misspoke. It's given as 2 by 64. Okay, in the
but
question. If you
with
take
2.
that, then you get one of these options, which is the correct solution according to this. Okay, have you tried it?
Yes, I think it
Yeah.
comes with 2 by 65, I think, not by
No,
2
2
by
by
60.
65, it gives the wrong answer, at least according to my algorithm. I have checked. Okay, so in this code, if you use 2
Yes,
by,
yes, you are right. 2 by
yeah,
65 gives wrong answer. Yeah.
yeah. So you should use this code with 2 by 64, while noting that ideally it
Sixty-five.
should be 2 by n plus 1, which is 65. Okay. In fact, I asked the person who made the questions, and he will look into it. But those you are attending, please use 2 by n, even though we know that it is random. It gives one of the options, which is the correct one. And anyways, if you use 2 by 65, you are not off to the answer, right?
Yeah,
It's close to one of the
but
options.
not very close. Means
Mm,
we
yeah.
cannot select the exact answer.
Mhm. Yeah, then use 2 by 64 for the time being. ठीक है. Oh, so we solved fifth one also. Was it number 2? Yeah, it was number 2. Given that we evaluate phi at what point? Is it 2 comma minus 4 or just a moment? Let me check. 2 comma 1. So if we use 2 comma 1, we get this with the boundary condition of nothing comma 0 being the left one is 4. Okay. But it's good, probably they realized this confusion. So this year there is no left, right, top, anything. You are just given indices which you blindly copy paste, and you get the answer. Okay. And if you are solving real life problem, then make sure that you stick to one convention. If you are taking transpose, then take transpose. Otherwise, just visually you can see which index corresponds to which one. That's all. Okay. Anything else? Anyone? Oh, right. By the way, I had asked professor to join, but he hasn't replied. I had asked him on Sunday. So today we are not having him. Most likely, I'll try to communicate with him this week, and we'll have him next week. Okay. And you must have received notification for the exams in announcement section. Yeah, so please look into this, and they also have demo for scientific calculator. So make sure you are comfortable with this. Like if you want to do 10 raised to 4, even I don't know how to do this. Maybe it's ulta. Yeah, then you have to press first 4, then 10. Okay, so just make sure you know how to operate this.
But this will be computer based, and this calculator and programming will not be there then. Means the way it was told in the previously when I asked, programming will be there. It was told, but
Yeah, so when I asked them, they said there will be 5 coding questions, and for that you will have some space to write Python program.
okay.
Okay,
Sir,
but
can you share last year's question, please?
last year's question.
Yeah.
Last means what are assignments you are solving? Means as a question only, no answer, but
No,
for
no,
practice.
previous year final questions of 70 marks.
The exam questions.
Yeah.
Yeah, I don't really have access. I just have access to this thing, the assignment questions, which I think you also have, right? Because I will upload it on the drive. I will ask them if they can provide it. Maybe they can upload it. So I also talked to them about the assignment solution for this year's after the deadline is over. So they said that they'll try to talk to NPTEL team, and most likely you will get solutions here itself on the portal. Okay, the coding questions, that is. Yeah. Anything else?
Arsh, that exam date is not going to be changed because, as we asked last time, it was on the same day of Diwali.
Yeah, then did you mail them?
I don't remember that.
No, I said I had sent you the mail, right, for the that thing. There was an email ID of Chennai IIT Madras NPTEL thing.
Yes, maybe that share on screen actually. I copied it, but I don't remember that whether I'd send it or not.
Okay, okay. I don't think the exam date is changed, but maybe I can let me copy paste the email ID in the chat box. Just give me a second. Support at nptel.iitm.ac in. So this was the response from Professor Mahendra Verma. I'm just reading out. I talked to NPTEL re-exam. They do not want to change the date. Ask the student to write to the NPTEL Chennai directly. Okay, and this was the email. So if you have any questions, you can directly shoot an email to this one. Okay. All right. Anything else?
These additional questions or something, if you can, similar lines, which especially for programming, if possible, means if it is available, not to make the questions, but if it is available.
Yeah, I don't really have them, but you can look it up online. There must
Okay.
be a lot of questions. Okay.
Yeah, yeah, will do.
Yeah. And you can use AI also to find similar questions, to get resources, etc. ठीक है. Anything else? All right, then let's meet next week, hopefully for the last time, and we'll do some miscellaneous things. Shall we solve the problem online during exam? Yeah, so they told me that there will be some space to write a code. I don't know you will be able to execute it or not. So that will clarify the next week when professor is there. Okay, because I'm not sure. How can we check the result? That I have no idea. I mean, I have zero technical knowledge about how NPTEL exam works because I'm not part of the process. But hopefully next week when professor is here, he would know, or at least he would let us know. Okay. Okay then. Chalo, bye bye everyone. Let's meet next week. Same link, same time.
Thank you.
Yeah. Thank you everyone. Bye bye. By the way, Nobel Prize was announced today, so please look into it what it was. Okay. Bye.